Hiding inside pretty much all of our important electronics, your surge protectors, your power supplies, you name it, there's this tiny unsung hero. It's a component most people have never even heard of, but it is the absolute last line of defense for your most valuable tech, everything from your big screen TV to your washing machine.
So what is it? Well, the answer is the Metal Oxide Varistor, or what we usually just call an MOV. This little guardian is literally designed to take the hit. It absorbs these violent bursts of energy so that your expensive gadgets don't have to. But how in the world does it actually do that?
Okay, so at its core, an MOV is what's called a voltage-dependent resistor. Now, that's just a fancy way of saying its behavior changes dramatically depending on the voltage it sees. Under normal conditions, it basically does nothing, just sits there. But the second a surge hits, bam, it springs into action.
The best way to think about it is like a pressure relief valve on a water system. When the water pressure gets way too high, that valve opens up and releases it safely so the pipes don't burst. Well, the MOV does the exact same thing for dangerous electrical pressure, which is, of course, voltage.
So what is going on inside this little component that gives it these incredible, almost magical properties? All right, let's crack one open and really take a look at its construction.
So if you look at a cross-section like this, you can see all the key parts. You've got that outer epoxy coating. That's for protection and heat management. Then you have the metal electrodes to connect it to the circuit. And right there in the middle, that's the heart of the device, a specially formulated ceramic disc. But the real secret, the real magic, isn't something you can see with the naked eye. That ceramic disc is made of countless microscopic zinc oxide grains, and they're all separated by these super thin boundaries of other oxides. These boundaries, that's the key. See, under normal voltage, they act as insulators. They block the current. But you hit them with high voltage, and they suddenly become conductors. It's an incredible switch.
So how do you even create a precise microscopic structure like that? Well, the manufacturing process is fascinating. It's kind of like high-tech pottery, and it demands unbelievable precision from the very first step to the very last.
It all starts with a very carefully measured recipe of metal oxide powders. This mixture is then dried out, it's pressed into that small disc shape we saw, and then it's prepared for the most critical step of all, firing it in a kiln. Only after that does it get its electrodes and that protective resin coating.
And when I say firing, I really mean it. During this sintering phase, those little ceramic discs are baked at scorching hot temperatures, sometimes reaching up to 1,200 degrees Celsius. This intense heat is what fuses the zinc oxide grains together, creating that all-important structure that allows it to work. Every single ingredient in that recipe has a critical job. The zinc oxide, which makes up about 90% of the core, that does all the heavy lifting. But it's the tiny amounts of additives, things like bismuth and cobalt, that form those magical grain boundaries that can switch from insulator to conductor. And that epoxy resin? It's not just for looks. It insulates the component and, crucially, helps dissipate the intense heat that's generated during a surge. So how does this incredible construction allow the MOV to do its job in a split second? Well, it's really a tale of two completely different states of being. In its normal, everyday state, just sitting there, the MOV has extremely high resistance. It's basically an open gate, totally invisible to the rest of the circuit. But when a surge hits, its resistance just plummets, and it instantly becomes a short circuit, creating a brand new, easy path for all that dangerous electricity. I mean, the sheer scale of this change is just mind-blowing. We're talking about resistance dropping from millions of ohms, mega ohms, down to just a handful of milliohms, all in a fraction of a second. As it does this, it diverts all that dangerous current through itself, and it heats up incredibly fast as it converts that destructive electrical energy into plain old heat. You can really see the process in action right here. On the left, during normal operation, the electricity just flows right past the MOV to your device. But on the right, when that high voltage spike comes along, the MOV suddenly becomes the path of least resistance, diverting that harmful surge safely away down to the grounding path. Now, it's really important to understand this. It's not a block. An MOV doesn't just stop a surge dead in its tracks. Instead, it clamps the voltage. What that means is it holds the voltage down to a safe, manageable level. So even if the incoming spike is thousands of volts, the circuit it's protecting only ever sees a much, much safer, lower voltage. And that's why selecting the correct clamping voltage is such a critical design choice for any given application. But, and this is a big but, this heroic act, it comes at a cost. An MOV is not invincible. Every single time it clamps a surge, it suffers a little bit of damage. It is fundamentally designed to wear out over time. Failure can happen in a few different ways. It can be a slow death by 1,000 tiny cuts, where each little surge degrades it until it just doesn't work anymore. Or it can be one single catastrophic event from a massive surge, like a lightning strike. The most dangerous failure mode, though, is thermal runaway. That's where a sustained overvoltage causes it to overheat, which is a serious fire risk. You might even see physical signs, like a cracked casing or black char marks on the board. So this raises a really obvious and critical question, right? If this component can overheat and potentially start a fire, why in the world would we put it inside all of our electronics? Well, the answer is teamwork. From a design perspective, you almost never use an MOV all by itself. It's paired up with a thermal fuse. This fuse's whole job is to monitor the MOV's temperature. If it gets dangerously hot, like in a thermal runaway event, that fuse blows, cutting power to the MOV and preventing a fire before it can ever start. It's a built-in safety net. So you see, an MOV's eventual failure, that's not a flaw in its design, it is the design. It is built to absorb damaging energy and to degrade over time because every single joule of energy it absorbs is one less joule that reaches your computer, your stereo, or your fridge. And this is exactly why safety protocols are so clear. You should always replace your surge protector after it takes one major hit. Ultimately, that's what the Metal Oxide Varistor is. It's a silent bodyguard. It works in the dark, it takes all the hits, and in the end, it gives its own life so that the devices we rely on every single day can live on. It really is a small sacrifice for a much greater good.